Hi everyone, Mr. Ang here. So today we are going to look at chapter 7, the kinetic particle model of matter. So in this chapter, we're actually going to take a look at how particles in matter behave, okay, and how this relates to the states of matter, and then afterwards, in the second part of this chapter, temperature and changes of state. So our learning outcomes here are to compare the physical properties of these different states of matter and to use this kinetic particle model to describe each of these states. And we relate the physical properties to the arrangement and the motion of the particles, as well as the forces and the distances between them. And then finally, we're going to learn about this new term called internal energy. It's an energy store that is made up of the total kinetic and potential energy in the system. Okay, I know that this chapter is coming out before we talk about the idea of energy, but we will talk about that in term 3. So, some basics. Okay, we know that all matter is made up of particles called atoms, and they can exist in solids, liquids, and gases. We're not going to talk too much about how the atoms combine to form molecules. We're just going to refer to either atoms or molecules as individual particles. Okay, and we also know from primary school science that properties of substances change when the substance changes state. So your liquids, solids, and gases, they are going to have different types of properties. So we're going to use this kinetic particle model to understand why our different states of matter have such different properties. But first, we have to understand, okay, this kinetic particle model. So here are some observations. We know that water can be frozen to form ice and can be heated to become water vapor or steam. How does this transfer of energy change the state? Okay, either by taking energy out of it to freeze it or by heating it to evaporate or boil it. And what happens to the particles, either the atoms or the molecules, when a substance changes state? This is the kinetic particle model. Okay, we're going to try and use this to explain what we observe. So, what is the kinetic particle model stating? It states that all matter is made up of tiny particles that are in continuous motion. This might sound familiar to you because in Sec 2, we already did a little bit of this when we talked about conduction. If you recall, we did a little bit of heat transfer where we did speak about how in particles, okay, sorry, in solids, we have particles that are constantly moving around and bumping into their neighbors. So this is very much the same idea. So on the right over here, this diagram is a visual representation of this model. Okay, this represents a solid with its particles in such an arrangement, as well as the forces between the particles. You may also be familiar with this because of some concepts that you've covered in chemistry, right? The giant molecular structure, for example. So in this model, these balls here represent the different particles that exist within solids, and these springs connecting the balls, they represent the forces that are between the particles and also how these forces store energy. So in our model, okay, our particles, because they are randomly moving around, have some form of kinetic energy. Okay, we've learned about kinetic energy in Sec 2, so this is the same idea. And because of the springs, okay, due to these forces between them, the particles also have some form of potential energy. So what happens when we transfer energy into this structure that represents our solid substance? When we do so, for example, by shaking it, okay, our particles will vibrate more vigorously because once we start shaking the structure, all the little particles inside will start moving and vibrating all over the place, and they will do so more vigorously. This increases the energy in the kinetic store, okay, or the amount of kinetic energy because the particles are moving more quickly, they have more kinetic energy. Next, as the particles are going to vibrate more vigorously, the springs that connect the particles, they are going to either be compressed or extended. And you should be familiar with this. If you played with springs, you know that when you compress or extend the spring, okay, you are actually transferring energy into the spring. You're giving it some form of potential energy. So it has elastic potential energy inside this spring. So when we have this kinetic energy and this potential energy, okay, that we are both transferring to the particles, we call this collection of energy the internal energy. Okay, why we call it the internal energy of a substance is because this is the energy that is contained within the substance itself. It is not like the kinetic energy of a substance when you throw the whole thing. Okay, let's say I take a block of ice and I throw it, that has kinetic energy because the whole block of ice is moving. However, internal energy is energy that the substance has even if, as a whole block of ice, it is stationary and, for example, you don't lift it off the ground, you don't give it some gravitational potential energy, okay, but it still has its own potential energy because of all these tiny springs or the forces between the particles. So that is why this is called the internal energy or the internal store of the substance. So as we continue to give the substance energy, we keep transferring energy into the substance, what is going to happen? Okay, the particles are going to vibrate more and more vigorously. And when they vibrate more and more vigorously, they're going to bump into each other more frequently, right? And they are going to push each other further apart. So that will cause a substance to expand. And this model actually also explains why when we heat a substance up, they tend to expand. Because what is happening? Our particles, like I said, they vibrate more vigorously, they push each other further apart. So when the particles are spread out further, the substance will become larger in volume. Furthermore, if you put enough energy into this substance, okay, the attractive forces may be overcome. You may end up putting so much energy into it that you are able to stretch the springs so far that they break. And then when that happens, the particles break away from their positions to roam freely, okay, because the attractive forces will get weaker with distance. So this is one part over here where the model does not align with reality. Okay, in real life, we know that springs usually the longer you stretch them, the more energy they have, the stronger the forces are. However, the attractive forces inside our particles, inside our substances, they get weaker with distance, meaning that as the particles get further and further apart, they are less attracted to each other. So, with enough energy, the particles will be able to break free from the substance and then they'll be able to roam freely. So you can see over here, this is a representation of the change of state from a solid substance to a liquid substance. On the left over here, you see that in the solid state, okay, my particles are arranged very regularly, very neatly in this pattern over here. Of course, this is not going to be every single solid substance. They are going to be arranged in this cube kind of arrangement. This is just a simple representation. But as we put more and more energy into this solid substance, what is going to happen? Okay, the particles will vibrate more vigorously, they will overcome the forces of attraction that are holding them together. And eventually, when that happens, enough of that happens, the particles will change their state to liquid because they break free. So you see over here on the right hand side of this diagram, okay, what we do have are particles that are going to be freely roaming inside the substance. They are not stuck in a particular pattern, they're not stuck in a particular arrangement, but they are free to move around. Okay, in the later slide, we will talk about how this actually explains the properties that we observe of solids, liquids, and gases. But you can only imagine here very simply that inside a solid state, because they are stuck in such an arrangement, that is why solids, okay, have a fixed shape. However, in liquids, they are not stuck in a particular arrangement, they are free to move around and flow around. which is why liquids do not have a fixed shape. So this over here you will see comes straight from the textbook and it's also in your notes. Okay, what we have over here are a quick explanation of a quick table to talk about the arrangement and the motion of the particles. Okay, so this is a good time to pause the video to copy it down if you need to do so. And with the arrangements, it also explains some of the properties that we observe. Because solids are closely packed and arranged in a regular pattern, they have the highest densities. They usually, when you take a substance, a solid substance, it has the highest density. When it changes state into a liquid or a gas, it has a lower density than its solid state. Then, when it comes to the motion, the particles vibrate about fixed positions. Because they are fixed in positions, they have a fixed shape and a fixed volume. The particles cannot move around freely. This arrangement of particles in this rectangle, they cannot suddenly decide to become a triangle. They are stuck with their neighbors. So this is because of all the strong attractive forces between the particles. Okay, so pause now. If you still need to copy, you need a little bit more time. Okay, and then you can start the video again on the next slide. Now, okay, so for our liquids, we see that the particles are less closely packed than in solids and they are arranged in an irregular pattern. So they are less closely packed, which means that they're a little bit further apart. So if they are further apart, that's why liquids have a slightly lower density than solids. Okay, compared to solids, liquids usually have a slightly lower density. Now, for the motion, the particles are free to slide over each other. They're not stuck in place anymore. Okay, previously, the solid particles, they had their fixed neighbors. However, now in liquid form, these particles, they're able to flow around, slide around, okay, because the forces holding them together, they are weaker than in a solid. You can think of them as in a solid, the springs are very, very strong, and that means that they're not allowed to move at all. However, in liquids, they're not so strong, so the particles can slide around. And that is why liquids have no fixed shape. They can change the arrangement and take on the shape of whatever container that they are in. Finally, in the gas, we have put enough energy into the substance that they have really overcome all the attractive forces. So they are very far apart from each other and they are arranged randomly, irregularly. Okay, they have the most energy. That is why we have to put in a lot of energy into a substance to get it to a gaseous state. And because they are so far apart, they have the lowest densities. There is very little particles, there are very few particles, okay, in a given amount of space. Now, for the motion, the particles can move freely in any direction. There are very, very few attractive forces, they are very, very weak. So, these are basically going to be able to travel in whatever way they want. And because of that, okay, they have no fixed volume and they have no fixed shape. I can take this collection of particles because there's so much empty space between them. It's not air, it's actually empty space. Okay, I can push them together, I can compress them and squeeze them together, and that is why they are compressible. And of course, they have no fixed shape because these particles can move in any given direction. They can fill up whatever container that they are put inside. Okay, so if you still need a little bit more time to copy down, okay, pause the video, and then once you're done, you can start the video again and we move on to the next worked example. So for the very first worked example, okay, you should describe and compare our three states of matter, solids, liquids, and gases, with regard to the average separation of particles and the motion of the particles. Now, in order to answer this question, we don't need to copy down exactly fully everything that was in the previous slides. Okay, on the previous page in that table, there's a lot of words, but we don't need to copy everything down. We just need the main key points. So what are these main key points? Okay, for solids, the particles are very closely packed together and they vibrate about fixed positions. For liquids, they are less closely packed compared to solids and they move freely within the liquid. For gases, they are very far apart and they move rapidly and randomly. Now, if you are asked, okay, to draw the representation of solids, liquids, and gases, just like what was in the table, okay, you can do so using some very simple rules. Okay, so maybe in addition to your answer, what I want you to do as well is to also draw the representation of the particles. So for solids, okay, we represent our particles with circles, but what I would like you to do is to draw them regularly and make sure they are touching each other. So you can see over here, they are very regular and they are touching each other. Okay, of course, when you draw, please use a pencil and then you can make it more neat. And this representation of solids, okay, will be a very clear representation of the fact that they are very closely packed together and they are in fixed positions. Because when they are arranged so regularly, so nicely, it shows that they're not able to move around within the substance. Now, for liquid particles, they are less closely packed together and they're able to move freely. So, how do we represent that with a diagram? Okay, what you could do is you can draw some particles, and instead of drawing them in a regular manner, what we could do is just draw particles close together, okay, touching as well, but you do not need to arrange them in any particular way. Okay, you can see over here they are randomly arranged, and this shows that the particles are able to freely move about while still being quite closely packed together. But you can see over here that there are a few more empty spaces between the liquid particles compared to the solid particles. And that is why they are less dense than solids. Now, for gas particles, how do we draw and represent gas particles? So very simply, the particles do not touch each other because we know that they are very far apart. So you can just draw a few particles scattered all over in a random arrangement, and that would be enough. Okay, there's no need to draw 10, 15 particles, okay, three or four, just in a random arrangement, that would be enough. So a summary of this lesson, okay, is that the kinetic particle model states that matter is made up of tiny particles, they are continuous motion, and we have used this model to explain our different physical properties of solids, liquids, and gases. We've also learned about internal energy that is made up of the kinetic energy due to the random motion of the particles and the potential energy due to the forces that are working between each of the particles. So in the next part, okay, in part two, we are going to look at how we can use this kinetic particle model to explain what happens when a substance changes state.